Bismillahirrahmanirrahim. The dot product. Usually in statics, we have to find the dot product. Occasionally in statics, one has to find the angle between two lines or the components of a force parallel and perpendicular to a lines. So this is one of the applications of dot products. In two dimensional, these problems will be solved by trigonometry, and geometry is easy to visualize. But in three dimensions, it is very difficult, and consequently vector methods should be applied for the solution. So the dot product, which is basically defines a particular method of we multiply two vectors and will be used to get the solution. Dot product, whenever we have two vectors a and b written as a dot b and read as a dot b, is defined as the product of the magnitudes of a and b and the cosine of the angle theta between them. If you can see the figure 2-41, you have one vector a and another vector b, and the angle between those two vectors is theta. So if you want to take the dot product of those two vectors, it will be vector a dot vector b is equals to ab cos theta. And one thing very important, theta is greater than or equal to 0 and less than or equal to 180 degrees. So the dot product is often referred to as the scalar product of vectors, since the result is a scalar and not a vector. So theta limit is very important. The theta must always lie between those limits. It must be greater than 0 and it must be less than or equal to 180, less than or equal to 180. Since it's basically we are taking the dot of two vectors, you have to be very careful that and it's basically the magnitude of a into b cosine of theta. So you know, whenever we have two unit vectors i dot I and their angle is going to be 0 degree, it will be the maximum. And if it's 90 degrees, and you know cos of 90 will be 0. So you have to be very careful in that when you are taking the dot of those two vectors. Here you have two vectors a dot b, and vector a is basically in Cartesian vector form given as axi plus ayj plus azk, dot vector b is bxi plus byj plus bzk. Now if you take dot product of these two vectors, it will be ax bx I dot I plus ax by I dot j plus ax bz I dot k. And then again, since over here I dot j and I dot k are two unit vectors with the unit angle between them is 90, so they will be automatically nullified and it will be taken as 0. When we get then the second line with plus ay bx j dot I plus ay by j dot j plus ay bz j dot k. Same logic applies over here. The first and third terms will vanish out and the second term will be there, which is ay by j dot j. And then we have another vector, third line az bk into k dot I plus az by k dot j plus az bz k dot k. The first two terms will vanish out, the third term will be there, and the end result will be the dot product operation of the results is a dot b is equals to ax bx plus ay by plus az bz. Then how to find the angle between the two vectors or intersecting lines? The angle theta between the tails of vectors a and b can be determined from as theta is equals to cos inverse of a dot b. These are a dot b are the vectors divided by the magnitude of a into b. The limit will again be theta greater than or equal to 0 and less than or equal to 180 degrees. Here A dot B is found from equation 2.13. We know what the relation is that in which we have multiplied the two vectors. If A dot B equals to 0, the cos inverse of theta equals to cos inverse 0 will be 90, and A and B will be basically perpendicular to each other. Then some very important points about the dot product is that we have already explained. It is you can calculate the angles between the two vectors or the projection of vectors in a specified direction. If vectors A and B are expressed in Cartesian vector form, the dot product is determined by multiplying the respective components, x, y, z components, and algebraically adding the results that we have already proved in the last slide. If you want to calculate the angle will be theta equals to cos inverse of vector A dot vector B divided by mod of those two vectors A and B. The magnitude of projection of those vectors along the line AA, whose direction will be specified by unit vector A, is determined by taking the dot product of vector A is equals to AA is equals to A dot of unit vector of A. Then we have a numerical over here, a very good numerical to determine how we basically apply the this methodology, how do we calculate the angles between those two vectors. Let's see this numerical. Determine the length of the side BC of the triangular plate. Solve the problem by finding the magnitude of RBC. Then check the result by first finding theta, then RAB and RAC, and then use the cosine law. Now if you look at it, this vector, you have got if you look at the figure, you have got x, y and z axis in the figure, and then if you look at it, you have to take it out the coordinates of B and the coordinates of C and the coordinates of the vector A. Now over here, if you are interested in first getting the coordinates of BC, the position vector, you will take BC. It will be, if you look at it, it will be 3i plus 2j minus 4k. You have to take out the coordinates of B. If you look at it, the coordinates of B is going to be on the x-axis, it will be basically 3, and then if you look at it on the y-axis, it will be basically 2, and then basically again if you look at it on the z-axis, its height is basically 4 meter. So in this way you basically calculate the position vector BC, 3i plus 2j and then minus 4k. So final coordinates minus initial coordinates, as we have already explained in the position vector. So RBC comes out to be equal to, if you take out RBC, it will be mod of RBC 3 square root of 3 pi whole square plus 2 whole square plus minus 4 whole square. It comes out to be equal to 5.39 meter. Also in the same way we are going to take out the position vector RAC. If you look at it, a position vector RAC, it will be 3i plus 4j minus 1k, and again you take the mod of RAC, it will be square root of 3 whole square plus 4 root whole square plus minus 1 whole square, and take out the square root, we will get it as 5.0990 meter. So we have got RBC, we have got RAC, and in the same way if you want to take out RAB, it will be 2j plus 3k meter, and its mod will be again square root of 2 square plus 3 square, it will be 3.6056 meters. And RAC, now what is going to do now is basically you are interested in, basically first you have calculated RABC, you have calculated RAC, but you are also interested in calculating the theta. For the theta, we know we have to calculate the angle theta. It will be between AC and AB. These will be the two vectors. So here we have to take the dot of these two position vectors, RAC dot of RAB. If you take, you already know what is RAC, it is 3i plus 4j minus 1k. What is RAB? If you know, it is 2i plus 2j plus 3k. You have to take the dot product of these two vectors. Since dot product of I do not have any other option, so we will go for the j's, which is 4 into 2 is basically going to be 8, and the k's is minus 1 into 3. So it will be basically 4 into 2 is 8 and plus minus 3. It gives you RAC.RAB gives you value of 5. Now what is the formula? The formula is theta is equals to cos inverse of RAC.RAB divided by the magnitude of RAC in RAB. So you put the values over there, and you, after inserting those values, you calculate the theta as equal to 74.219 degrees. So this is our theta. Now you basically, once you calculated this, you can also calculate this by using the cosine law. If you want to take the cosine law, you know already that in the cosine law we take the angle which is opposite to the resultant. We just calculated theta as 74.219, so we can take it as RBC and the root of square of one side plus the square of the other side minus 2 square of one side minus 2 times the length of the one side, length of the other side, and the resultant of the angle of the is basically cos 74.219, and you can see the same result appears. RBC is equals to 5.39 meter. Then again we can go determine the projection of the force F along the pole. You have to do the projection of this force which is in the Cartesian vector form along the pole. If you look at it, we know the projection of the force F will be basically this force F vector, and you have to take it along the pole, and the pole is, you have already given O to some point. So here if you look at it, we will take the dot product of this vector F which is given as 2i plus 4j plus 10k dot, and we have to take the unit vector along this vector from O to the point where the pole is ending. If you look at it very clearly, the unit vector of this, you have to take the coordinates. If you look at the coordinates, we have on the x-axis from O we travel 2 meter, on the y-axis we travel again 2 meter, and then we have to travel down, which is 1 meter. So our coordinates will be 2, 2, minus 1. So if you look at it, and basically when we have, so we can also take the mod of from O to the point the pole ends, it's going to be basically square root of 9. So you can see we take the dot product of force F dot the product of UA, which is the unit vector along the line of the pole. So it is 2 upon 3i plus 2 upon 3j minus 1 upon 3k. So if you look at it, we take the dot product 2i dot of 2 upon 3i plus 4j dot of 2 upon 3j, and then 10 into minus 1 upon 3k, and we basically algebraically add them, and we get up to the result as projected force F is equals to 0.667 kilonewton. Let's go to another numerical. If the resultant force Fr of two forces acting along the log is to be directed along the positive x-axis and has a magnitude of 10 kilonewton, determine the angle theta of the cable attached to B such that the force Fb in this cable is minimum. What is the magnitude of the force in each cable for this situation? So again, if you look, you have got force Fa and you have force Fb, and you have got and the angle between the x-axis and force Fa is 30, and the angle between Fb and force x-axis is angle is theta. So if you look at it very clearly, it is a very simple case for law of parallelogram, law of forces. So in order to provide a minimum force Fb, as they have asked us, we need to determine the angle theta which is attached to B, and that this force is a minimum. So what we should do is to make this force a minimum. If you know it very clearly, to produce a minimum force Fb has to act perpendicular to Fa. So the parallelogram law of addition is shown in the figure A. FA and FB, and you can see the angle between FA and FB comes out to be is 90 degrees, and the resultant is basically calculated as they have given in the numerical. It is 10 kilonewton. So now if you look at it, you can basically take out a triangle out of that parallelogram, which is FA and then FB, and the resultant is 10 kilonewton. One is 30, and you know the angle from figure A is FA and FB angle is 90. So in the triangle that we took out, you can see the angle between FA and FB is 90, and the unknown angle which was between the resultant and the FB is theta. So by trigonometry, you can now very simply calculate it as what will be FB. FB will be equals to 10 sine 30 is 5 kilonewton. FA is 10 cos 30, 8.66 kilonewton. And once you've got this thing, you can calculate the angle theta. The angle theta is 90 degrees minus 30 degrees is 60 degrees. So here it is. We have solved this numerical. Now we go to another numerical. If theta is equals to 60 degrees and F is equals to 20 kilonewtons, determine the magnitude of the resultant force and its direction measured clockwise from the positive x-axis. So if you look at it, you have got an xy coordinate system. You have got one force 50 kilonewton, and the other force is 40 kilonewtons, and one force which is in basically in the third quadrant, force F. It's making an angle of theta with the negative x-axis. So what can we do? How to solve this problem? We will resolve it into its components, and then we will add the like components together to get the resultant force and the theta. The other thing which is very clear over here is that you see this 50 kilonewton force angle is not defined, but if you see its vertical angle could be calculated as 3 upon 5, and its horizontal angle along the x-axis could be taken as 4 upon 5. So they are basically showing the angles. So in this way, if we sum up all the forces, Frx equals to sigma Fx, we will get Frx is equals to the 50 kilonewton force, and what will be the x? Its the orientation along the x-axis. It will be 4 upon 5. Then we go to the other component of the force, which is plus the 40 kilonewton force, and what will be its component along the x-axis? It will be 1 upon root of 2. And then we go to the force which is making an angle of theta along the negative x-axis. So it is that force F is basically component is 20. It is given as F is 20 kilonewton, and the angle will be cos 60. But see, it's not saying plus 20 cos 60. It is saying minus 20 cos 60. Why is it saying that? If you look at it, the direction, if you resolve it into its components, the component along the x-axis will be in the negative x-axis. So that is the reason it is showing a negative sign. Now you add up all those forces, the 50 kilonewton force component, the 40 kilonewton force component, and the force F, which is 20 kilonewton force component. You add all those components and you will get it as 58.28 kilonewton. Now we go the vertical force component Fry is equal to sigma Fy. Let us take the y components. For 50 kilonewton force component, it will be 50 kilonewton into multiply by 3.5. Then we go to the other component, the 40 kilonewton. It will be 40 kilonewton 1 upon root of 2. But you can very easily see that its orientation is on the negative side compared to the y-axis, so minus. And what about the 20 kilonewton force? It is 20 sine 60, but again it will be the orientation of this force component is along the negative side from compared to the positive y-axis. So you add up all those components of y forces, y components of the resultant force y, it will come out to be equal to minus 15.60 kilonewton. So you got Frx added up as 58.28 kilonewton, and you got Fry added up as minus 15.60 kilonewton. Now you are interested in the resultant force, as the questioner have asked you what is the magnitude of the resultant force. The magnitude of the resultant force is very easily calculated as Fr is equals to under root of summation of square root of under square root and then under root of fx square, fx ka whole square plus fy ka whole square. What is fx the whole square? It is 58.28 whole square plus what is fry the whole square? It is minus 15.60 the whole square. So you calculated fr as 60.3 kilonewton. Now he is also asking you that you need to calculate the theta from the positive x-axis. So theta will be tangent inverse of fry. What is fry? 15.60 upon 58.28. So it's again it will give you the absolute value, and absolute values from the mod will be positive. So theta comes out to be equals to 15 degrees. But remember, this theta is basically the orientation of FR from the positive x-axis. So this is another very good numerical. It will give you more concepts about how to solve it. Let's go to another problem. Express each of the three forces acting on the column in Cartesian vector and compute the magnitude of the resultant forces. So you have basically need to calculate each of these three forces which is acting in on the column. A column basically takes the load. You can see in your home you will have every uh, room have like 4 columns for to take the roof of the take the load of the roof. So and you compute the magnitude of the resultant force. So one force is F1 is 150 pounds. Again its orientation is given. Then there is an F3 force 75 pounds. Its orientation is given at 360 degrees along the x. Then there is a very unique force. If you look at it, it is F2 is equals to 275 pounds. But it has actually no orientation and it is exactly lying on the y-axis. Now, how to solve this? Very simple. You will take F1 and you will take because what will be the components of F1? F1 is equals to 150. The x component will be 3 upon 5 I, and what will be the y component is 150 4 upon 5 j. But if you look at it, the sense of a vertical component of F1 will be opposite to that of the positive y-axis. In the last, remember exactly the same way we did the last numerical. So we'll take minus 154 upon 5j. What will be then simplify it? We simplified F1 is equals to 90I minus 120j, and the resultant force unit is pounds. And again, this force is basically represented in Cartesian form, not in a scalar form like F1. For example, we say F1 is equals to 30 pounds or 200 pounds. No, it is 90I minus 120j. This is a Cartesian vector form, and they have clearly explained us in that possible way. Then you go to F2. F2 is basically minus 275 j pounds. We have just directly put it. We do not have any components, but you see along with 275j we have added F2 with a negative sign. Why? Because see, the orientation of F2 is opposite to that of the y-axis. So F2 is minus 275 j pounds. Then we go to F3. If you look at it, F3 is basically will have two components. One is will be 75. The x component will be 75 cos of 60I, but you resolve it into its components. You will have two components. See, the orientation of x component will be lying towards the negative x-axis. So it will be minus 75 cos 60I. And what will be the y component? You see that y component will always be orientationing along the negative y-axis. So minus 75 sin 60j. So F3 comes out to be equals to minus 37.55 minus 65j pounds. So you got F1, F2, F3 forces in Cartesian vector form. Now how to solve them? How to get the actual results? Very simple. Simply add all the I components together and simply add all the j components together and you will get your Fr, and Fr will be equals to sigma F is equals to 52.55 minus 460 j pounds. So you want to take it, and again this force is basically in Cartesian form. If you are interested to get what will be the value in the scalar form, you can take it as Fr is equals to under root of 52.5 whole square plus minus 460 the whole square and take the square root. So you will get Fr is equals to 463 pounds. So this is a good numerical. Hope you will be able to understand these concepts and getting better and better with every numerical. Let's go to another numerical. The top one, again it is showing you uh, the pole is subjected to the force F, which has components acting along the x, y, z axis as shown. If the magnitude of F is 3 kilonewtons and beta is equals to 30 degrees and gamma is equals to 75 degrees, determine the magnitude of the three components. So again this is basically another numerical which is of related to which topic? Direction cosines. Yeah, and you know the mathematical formula to solve this numerical is the formula of direction cosines is as explained in the previous week 1 theoretical lectures is cos square alpha plus cos square beta plus cos square gamma is equals to 1. Okay, now they have given us beta and gamma is being given to us. So if beta and gamma is here, we can put it as cos square alpha plus cos square 30 plus cos square gamma, which is 75 equal to 1. We will get alpha is equals to 64.67 degrees. Now this force F, whose magnitude is given to us as 3 kilonewton, is a three-dimensional force. So it will have one component along x-axis, one component along y-axis and one component along z-axis. Now you know in direction cosines the component of this three-dimensional force F along the x-axis will be which one? The alpha. The component of the force F along the y-axis will be which component? It will be the beta, and the component of this force F along the z-axis will be the gamma. So you can see Fa is equals to 3 cos 64.67. It comes out to be equals to 1.28 kilonewton. If you say Fy is equals to 3 cos 30, it comes out to be equals to 2.6 kilonewton. And what about Fz? It is 3 cos of gamma, it is 3 cos 75, it comes out to be equal to 0.776 kilonewton. So this component numerical related to us as direction cosines. Now you express the position vector r. Another numerical, we go to express the position vector r in Cartesian vector form and determine its magnitudes and coordinate direction angles. So the position vector r you have to express in the Cartesian vector form, and it will be from where to where? It will be from the A to the B. So you have to take that position vector r. You have to basically simply calculate the coordinates of A and you have to calculate the coordinates of the B. So if you look at it, we have basically the coordinates of 8b will be like b minus a. So they have taken out as the position vector. It comes out to be equals to 6 minus 2i plus 6 minus 2j plus 4 plus square bracket open minus 4 k. So you have to take it out. If you look at it, how you have done it, just to make it easy for you, look at what will be the orientation of A. If you look at it, you move 2 feet along the x-axis, and then if you see, you move again 2 feet along the y-axis, but that is on the minus side, and then you move 4 feet along the y-axis, which is along the z-axis, which is the positive z-axis. So that is why if you look at it, it will be 2 minus 2 and 4. You can see it will be 2. For coordinates A is 2 minus 2 and 4. They have calculated it like this. If we wanted to take out the coordinates for example say B, so if we move, you can see from the origin you start to move towards the x-axis, it will be 6 feet, and then you move to from 6 feet you again move on the y-axis, it will be again 6 feet, and then along the first move 6 feet along x-axis, then move 6 feet along y-axis, and these are positive distances. But then 4 feet is basically along the negative side of z, so it will be like 6, 6 and minus 4. You calculated it like this. So that is how you take the coordinates. You have to be very careful when taking the coordinates of three-dimensional system. Now you take position vector. Position vector again is comes out to be equals to 4i plus 8j. Again, how you take it? Coordinates of b minus the coordinates of a. It's basically RAB. You can take the other way around also. It's not a problem. But so you take the position vector as r comes out to be equals to 4i plus 8j minus 8k, and since it is a vector, its length is feet. Position vector. Then the magnitude of r is comes out to be equal to, you take the square of 4 square plus 8 square plus minus 8 whole square. It comes out to be equals to 12 feet. Now you are interested in the coordinate direction angles. It will be, and you know what are the coordinate direction angles? Alpha, beta and gamma. Cos alpha, cos beta, cos gamma. So cos alpha, if you look at it from the values of the r, it is 4 divided by the magnitude 12. It gives you cos alpha. Alpha is 75 degrees. Then cos beta, it will give you 8 upon 12 degrees as 48.2, and cos gamma will give you minus 8 upon 12 as gamma is equals to 132 degrees. These are the direction cosines of the coordinate direction angles of the position vector AB. Then again, so far what we have done, it is a very simple chapter, chapter 2, just to give you a complete flashback of things, just to, so that you may not forget, and just summarize the things. It is very important. At the end of chapter you will have a review. It will give you basic ideas which you might have missed, like what is a scalar, what is a vector, how do you multiply the vector, and again I have told you these things in your previous lectures, theoretical aspects. If vectors are collinear, the resultant is simply the algebraic additional sums. Parallelogram law of forces I have defined you. Any two vectors can be basically solved by parallelogram law of forces. Direction cosines. Then sorry, you have to use a cosine law as fr is equals to f1 square plus f2 square minus 2 f1 f2 cos of theta r, and theta r is the angle which is opposite to the resultant. Then you can also use the sine law to find those unknown forces. The resultant are basically the orientation of those forces are resultant by means of sine law as f1 sine theta 1, f2 sine theta 2, and f is equals to f r sine theta r. Then rectangular components in 2 dimensions. I have told you about whenever we have two vectors, we can also use the direction cosines and sine law for finding those unknown components, but we can also make it easy. You can solve the same numerical by means of rectangular components in 2 dimensions. And what we do, as we have done in the previous numericals, I have told you that you resolve it into its respective components, x, y in 2 dimensions if it is z, and then z component in 3 dimensions, and you simply add the like components together to get frx, and you add the y components together to get the fry, and so frx equals to sigma fx, fry equals to sigma y, and fr is equals to summation of frx the whole square plus fry the whole square. It will give you fr, and theta will be equals to tangent inverse of mod of fry upon frx. It will give you theta from the positive x-axis. Then Cartesian vectors, I have told you the unit on every vector orientation can be given as unit vector. The unit vector u has a length of 1, no units and its points and direction of vector f. So any vector divided by its magnitude will give you a unit vector. Okay. So a force can be resolved into its Cartesian components along x, y, and given as f equals to fxi plus fij plus fzk. And the magnitude of this force is equal to under root of fx squared plus fy squared plus fz squared. And if that force is basically lying not in a 2-dimensional system but in a three-dimensional system. So the how to calculate that those two force, again you take a unit vector f upon f, vector f divided by its magnitude f. It can be that f can be resolved into fx upon fi plus fy upon fj plus fz upon fk, and the unit vector along those can be given as cos alpha I plus cos beta j plus cos gamma k. This is also a very important equation frequently used uh, in basically solving direction cosine problems. Then again we have in coordinate direction angles, we know that there is another important relation to be used is cos square alpha plus cos square beta plus cos square gamma is equals to 1. So two of the three independent angles are independent of one another. The coordinate direction angles are related so that only two of the three angles are independent of one another. To find the resultant of component force system, express each force as a Cartesian vector and add ijk components of all the forces in the system. If you have got a position, again position vectors, if you want to calculate it, you have position vector a and b, you can take the coordinates of b and subtract the coordinates of a, you will get the position vector AB, as I told you in the numericals also. Then if there is force F which is acting, you can also always express that vector force F in terms of magnitude of force into, you take a unit vector on that force F. It will be in that form of position vector acting on that force. Like over here is F into U, and U could be represented as position vector R divided by its magnitude. Then again we can also take it as dot product. If you have a dot product, it will be a dot b is equals to ab cos theta, and if you solve those two vectors by means of dot product, it will be ax bx plus ay by plus az bz. In the same way, if you got theta, theta will be equals to cos inverse of a dot b vector divided by ab. And if you got you could use to determine the projected components of vector A onto any axis, you will use A is equals to a cos theta into unit vector along the projected axis. So this is basically all about the chapter 2. We have done the theory first, some numericals, and then in the end we have also basically done a lot of different types of numericals, and then we have got a brief review on what we have done in the chapter 2. In the next we will be starting with the chapter 3 and equilibrium of the particle, and we will be showing you some pictures and numericals and theory of that chapter. Thank you.